In this video, we're going to be looking at X-ray diffraction, Bragg's law, and the reciprocal lattice. So this is going to be building upon a lot of what we did in the previous video, which was an introduction to condensed matter physics, looking at crystals and looking at some of the basic properties of crystals. And things are going to start getting quite complicated, and towards the end of the video, things are going to become quite abstract. So that's a fair warning. We're going to be looking into how X-ray diffraction in crystals actually kind of gives us this entire framework for understanding the physics of condensed matter. So this will be quite an important video, and many of these concepts will at first seem incredibly weird, but will become very, very relevant later on when we come to do more advanced physics. So without further ado, let's go ahead and jump right into it. Okay, so the first thing we are going to ask ourselves is we have our crystal, and we obviously know that the crystal structure looks like this. We know this from looking at it under the microscope. But how do we probe the crystal structure exactly? How do we actually get this exact kind of dimensions right here? Well, interestingly, it was actually the discovery of X-rays that actually enabled us to determine more about how crystals are structured. So X-rays were discovered in 1895, and they had a key property, which was because they are in a high energy part of the electromagnetic spectrum, they're able to pass through materials very easily and are invisible to the naked eyes. So typical wavelengths of X-rays are around 0.01 nanometers, and they go all the way to 10 nanometers. And essentially they can be used in order to probe a crystal structure. Now, essentially the way this worked was that you had some X-rays that were traveling towards a crystal. So say this is your crystal structure, drawn quite crudely, is you would observe a interference pattern under the microscope. And the interference pattern looked something a little bit like this. You have a central shape in the middle, and then you have a sort of ring of dots around the outside of the center. And then you have more rings of dots even further away from the center. And this you guys may be able to recognize as an interference pattern. And this actually showed that X-rays were waves. They were in fact electromagnetic waves, which settled a long-standing controversy as to what X-rays actually were at the time. And it was actually a physicist called William Bragg who proposed that the pattern was due to interference effects, so wave-like interference effects. And his argument was that a crystal structure could be considered as planes of atoms kind of layered on top of each other. So let's go ahead and draw out his kind of schematic. So essentially you've got these are lattice points right here, but of course there's going to be atoms attached to them. He essentially kind of considered the atoms to be arranged in planes right here. So you can kind of draw a plane that kind of cuts across one row of atoms. And his theory was that when you sent X-rays coming into the structure, they simply ricocheted off, they reflected off the planes. And of course, if the X-ray source is sufficiently far away, the X-rays you can kind of consider to be parallel rays that are traveling towards the crystal planes and then just kind of bouncing off. So let's go ahead and label this diagram. So here is, of course, our kind of reflection normal. And let's go ahead and assign this angle to be angle theta right here. So we can say that the X-rays are traveling at an angle theta relative to the horizontal axis. And our X-rays are traveling down in this direction right here. And then they are bouncing off the planes and leaving in that direction right here. Now, let's go ahead and label this distance between two planes D for now. We'll come on to this a little bit more later on in the video, but let's go ahead and just call it D. Now, hopefully you guys are familiar with some of the basics regarding diffraction and constructive interference effects. And hopefully you guys will be aware that within diffraction, you'll get an intensity peak where there is constructive interference between two wave sources. So essentially we have two different wave sources that are going to be interfering with each other in order to produce an interference effect. And then what we can say is that for constructive interference, the path difference, so that is the difference in distances in which the two rays have to travel, has to be equal to an integer number, n, multiplied by the wavelength of the beam. So again, hopefully all this is fairly familiar if you've studied diffraction before. In order to get constructive interference, the path difference between the two waves has to be an integer number of multiples of lambda. And if you want to get destructive interference, it has to be a half integer. But yeah, we're talking about constructive interference. The path difference has to be an integer number multiplied by lambda. So what is the path difference? Well, let's go ahead and have a look at these two paths right here and see what the difference is between them. Essentially, these two beams are completely in phase until this point right here. And at this point right here, this beam, this top beam, bounces off this plane right here, but this beam continues traveling forwards for a little bit. So what is that kind of distance between here and here? Well, we know that this distance right here is d, and we also know that because this angle right here is theta, we can also label this angle here as theta, and because this angle is 90 degrees, this angle is 90 degrees, and therefore this total angle must be 90 degrees. Therefore, this angle is 90 degrees minus theta, and this angle right here, a little bit hard to draw right there, is also going to be theta. So using trigonometry, sine, cos, and tan definitions, we can write that this side right here is actually d times sine of theta right here. So that's this distance to this distance. This is d sine theta. But of course, before it becomes back in line at this point right here, it also has to travel another distance d sine theta right here. So the total path difference between these two waves right here is 2d sine theta. And this is equal to an integer number multiplied by lambda, the wavelength of the X-rays. And this right here is known as Bragg's law, unsurprisingly. And this is a very important relationship. This relates the distance between planes to the probing wavelength lambda. And this actually kind of gives us a sense for how far apart the atoms are. It's going to be something along that kind of length scale right there. And this is quite an important relationship, and it's very, very useful for probing inside materials. Now, I want to kind of consider the planes a little bit more, because of course I have just drawn a very simple example where there are planes that connect rows of atoms. However, planes can get quite geometrically complicated within crystals. And so there's actually a system designed to notate various types of planes within crystals. And this system is known as Miller indices. Now, I'm not going to lie, these are pretty confusing, to be honest, at first, and very unintuitive for how they work. So I'm going to go through and try and explain them in a way that kind of makes as much sense as possible, at least to me. It's a very weird notation system that I'm honestly not a huge fan of, but I've kind of come up with a way of sort of visualizing it in a way that can hopefully make sense. So let's go ahead and jump into 3 dimensions right here. So we have our 3 axes right here, and this is going to be a unit cell of a 3-dimensional lattice structure. So because it's a unit cell, this length right here is going to be A, this is going to be B, and this is going to be C right here. So what I'm considering is a cubic cell in 3-dimensional space. And let's go ahead and consider a simple example of a plane that is going through this cell. And the first one I'm going to consider is a plane that is basically kind of going along this face of the cell, the cube right here. So I'm going to just shade it in. So there is a plane that technically extends all throughout the crystal, but within this cell, this plane is going along sort of this position right here. So how do we notate this plane? Well, what we can do is we can consider whereabouts this particular plane cuts the three lattice vectors, A, B, and C. So how far along those three lattice vectors does this plane cut? Well, we can see that along A, it cuts it all the way through. So it cuts it at this point right here. So it's 100% of the way along A. And what we do is, rather than write the fraction of this vector at which the plane cuts, we actually take the reciprocal. In this case, the reciprocal of 100% or 1 is just going to be 1. So therefore, this plane we write for its first index, its first Miller index, we write as 1. What about the B component? Well, we can see that this plane right here, this is along this face of the cube, we can see that this does not intercept with the B vector right here. So what this is kind of equivalent to saying is that it intercepts at infinity. So this is a bit of a hand-wavy argument, I'm aware, but you can kind of say that rather than not intercepting, we can say that it intercepts at infinity. And therefore, if you take the inverse of infinity, what do you get? 1 divided by infinity. Again, maths people would probably have a huge problem with this argument, but we can just say 0. So 0 essentially means that it does not intercept that particular axis right there. And of course, same goes with C. This plane, again, does not intercept this line, this axis line right here. So therefore, the Miller index for this plane right here is 1, 0, 0, and we technically put it in brackets. So let's go ahead and do a few more examples, because I think the best way to understand these are with lots and lots of examples. So let's go ahead and draw out our unit cell once again. Now I'm going to draw a plane which goes kind of diagonally across from this edge of the cube to this edge of the cube. And I'll just shade it in. So let's go ahead and ask the same question. Whereabouts along A does it intercept? Well, it intercepts along A right here at 100% of the way through. 1 divided by 1 is 1, and that's our first index. What about B? Well, this time we can see that it intercepts all the way along B. So yet again, 1 divided by 1 is 1. And C right here, yet again, we can see that this plane does not intercept C whatsoever. So therefore, we can kind of say it intercepts at infinity. Therefore, 1 divided by infinity is 0 right here. So let's now go with a more complicated example. So let's go ahead and apply the same logic right here. So we can see that along A, we can see that it does not intercept the A vector right here whatsoever. So therefore, we can say that this first index is going to be 0. What about B? Well, we can see that in this case, it intercepts halfway along the B vector right here. And because it intercepts halfway along, we take the inverse of a half. What do we get? We get 2 right here. So 2 is our second Miller index. And what about C? Well, we can see that for the C vector, it intercepts all the way along, 100% of the way along. 1 over 1 is 1. So this is going to be 1, and this Miller index is going to be 0 to 1. And one more example, in this case, we're going to look at this plane right here. So obviously this is a bit more geometrically complicated, and we can see that its normal is actually kind of pointing out this way, off a sort of weird diagonal angle. So let's go ahead and do the same logic. What about A? So we can see that for A, along the A vector, it intercepts halfway along. Therefore, our first Miller index is going to be 2. And for B, we are going to see that it intercepts 100% of the way along. And actually, same goes with C. So the indices for B and C are going to be 1 and 1. So we have this is a 2, 1, 1 plane. Now, where it gets a little bit messier is when you start to have negative numbers involved. And this took me a little bit of mental jiggery-pokery to try and sort of figure out how this works. So let's go ahead and take this plane right here. Well, in this case, we can see that it intercepts with the b-axis kind of halfway along. So that's kind of fairly counterintuitive. But in terms of intercepting the a-axis, it intercepts at 0 right here. And in terms of intercepting the c, well, this entire plane seems to be along the c line. So it kind of intercepts absolutely everywhere. So this is a bit kind of weird. How do we kind of like work with this? Well, essentially what we have to do in this case is kind of move, consider the cell which has a plane which doesn't actually kind of cut through the entire axis right here. And the one which doesn't do that is going to be the one which is to the left of this cell right here. So we basically have to kind of move it off of a particular axis. So let's go ahead and draw in the plane which is formed from the adjacent cell. Because of course, remember that the planes are, of course, in every single cell. I've just only chosen to draw one cell in particular. Okay, so here we go. There is our adjacent cell right here, which we're going to have to consider because, of course, this plane intercepts the entire axis right here. So what would be our indices in this case? Well, we can see that in this cell right here, you can kind of think of it as the a vector kind of intercepting at this -1 right here. So of course this would be 0, this would be 1, sorry, this would be 0, and this would be -1. So you can kind of look at it as intercepting at -1 rather than 1. And in order to represent negative numbers, you actually put a bar on top of the negative number. So our first index in this case would be 1 bar. Again, bit hard to understand that one, but if you find that your plane intercepts with the origin point, then you have to consider the next one along. What about our B? Well, thankfully B won't change. Our point in which the plane cuts along the B axis won't change either. In this cell, it should be the exact same. It's going to be halfway along. I didn't do a very good job of drawing it, but this is in fact halfway along the B vector right here. So 1 divided by a half is therefore 2. And what about the C? Well, we can see that in this plane right here, it in fact never intercepts with the C vector right here. So therefore we write 0. So whereas before it was intercepting all the way along, if we consider the next one along, it doesn't intercept at all with the C vector. So that's kind of how you can sort of use negative numbers in Miller indices. Again, these are a bit messy to understand. That's kind of my method of going from a plane to notating it using these indices. And the whole point of doing this is that with our formula that we had earlier, n lambda equals d sine theta right here, this d term right here, I said was the distance between planes. And as you can see, this d represents that distance there between two different planes. And of course, you can have any number of planes within the crystals. It kind of depends on what plane you're choosing to analyze. But this d right here is, in fact, the plane determined by the 3 Miller indices. And so in order to just notate that, we can just write n lambda is equal to d HKL, where H and K and L are the Miller indices, so they're these 3 numbers right here, times the sine of theta. So this is the distance between Miller planes right here. And just as an example, for cubic crystals, the distance between HKL, you can actually write that as A, which is the lattice constant. Remember this, and this would actually be the same for all 3 lengths of the cube. And this would be divided by the square root of h squared plus k squared plus l squared. So obviously, if your plane only has 1 Miller index, so if it was this plane right here, you can kind of clearly see that the distance between adjacent planes would just be a divided by square root of 1 squared plus 0 squared plus 0 squared, which would simplify to just a. So the distance between these 2 planes, of course, is just going to be the lattice constant itself. So all of what we've discussed so far has been regarding classical physics. We have not yet, in our condensed matter physics journey, delved into the realm of quantum mechanics. And it's actually through this next section, which we're going to explore, where we can actually generate this framework, which is going to have an intrinsic connection to quantum mechanical states. So essentially, we've looked at how the planes can produce a diffraction pattern when observed through a microscope. And we can calculate the positions of these peaks by using the distance between Miller planes, dHKL, as our distance. And we know that relation using Bragg's law. But we've not yet touched upon the intensity of these peaks, and it's actually through this next bit where things are going to start to get very, very interesting and, dare I say, very, very abstract. So let's go ahead and jump into it. So we are going to go ahead and jump into Fourier analysis. Now, this isn't a maths channel, this is a physics channel. The mathematics of Fourier analysis go very, very deep, and it's a very complicated area. We're actually only going to use a very small part of Fourier analysis for this, but we're going to use what we need to in order to understand what's happening inside a crystal structure. So first of all, what is Fourier analysis? Well, the easiest way to kind of understand what Fourier analysis is if we have, say, some kind of wave, some signal that's come in. So we have a very random, noisy signal that is being sent to us. Maybe this is a voltage signal, or maybe this is a sort of light signal, or anything which can resemble a wave. You'll notice that this signal is very noisy and very messy. And what Fourier analysis does is essentially decompose this entire wave structure right here into very, very basic wave forms, which are sine and cosine functions. So a sine function, as I'm sure all of you guys know, is one that starts at 0 and oscillates like that. And a cosine function is very, very similar, except it's been shifted by 90 degrees or pi over 2 radians, and starts at 1, and after one full period, it ends at 1. Now, of course, when we're dealing with sine and cosine and tan and all other trigonometric functions, we, of course, want to work in radians. So we say that one full period is 2 pi radians. So this is cosine of our variable x, and this is sine of our variable x. And essentially, we can write this giant messy wave in terms of a summation of sines and cosine functions. And I'm going to write out the general formula for this, and then I'm going to go through and break down what each term in the formula actually means. So let's say this right here is our function, f of x. Then f of x is going to be equal to a constant term out the front plus the sum going from n equals 1 to potentially infinity, and this is a very general formulation, an times cos n pi x divided by L plus bn times sine n pi x over L. So let's go ahead and break this down. So this first term right here, a0 over 2, we notice this term is outside the summation. And this is actually for good reason. This term simply provides an offset for our function. Obviously, if we know that we add a certain constant to our function, we simply change whereabouts it intercepts with the y-axis. And so this is what this function does. And then we have this summation term right here. This is a very general way of writing out all of the various components, if you like, of sine and cosine functions, which can add together in order to produce our very, very complex function right here. So there is a cosine term and a sine term, you'll notice, and essentially these can kind of be considered orthogonal to each other. They're actually what's known as linearly independent, and what that basically means is that if you add further cosine terms, it does not affect the value of any sine terms. Sine and cosine can be essentially considered linearly independent. They're at 90 degrees with each other, or pi over 2 radians, almost literally. They're pi out of 2 radians out of phase. Now, the next thing to consider is odd functions and even functions. Now, an odd function is essentially defined as one where f of minus x, so if we take the negative of the argument x, is equal to minus f of x right here. And a simple example of this would be y equals x, where say x is 3. If x is 3, then y is 3. Then if we negate the x term, the x argument, and say that x equals minus 3, then y will also be minus 3. So whatever you do to the argument term, then y will simply be negated in a similar way. However, an even function is mathematically defined as one where f of minus x, so this time if we negate the argument, we actually just get f of x right here. And an example for that would be y equals x squared. And this would only be true for real numbers, obviously. But essentially, 3 squared is equal to 9. If we take the negative of 3, we get minus 3. And minus 3 all squared is still equal to 9, because minus 1 times minus 1 equals plus 1. So that is an odd and an even function. And you'll notice that sine and cosine actually follow a very, very similar pattern. Sine, as you'll notice, is an odd function. If we negate the argument of sine x, so sine of minus x, then we will get minus sine of x. And similarly, with cosine, if we negate the argument of cosine of minus x, then this will equal cosine of x, because it is an even function. And the key thing to bear in mind with this is that if you have an odd function, if your random noisy function is odd, so for example, if you wanted to write out y equals x, which would be this function right here in terms of sine and cosine, then you know that there would be no cosine terms in your summation. It would only include sine terms, because this cosine term essentially counts for evenness, and this sine term essentially counts for oddness. And now we can get into what an and bn are, because these are weighting coefficients essentially. So these kind of determine how much cosine and how much sine for a given n value, which essentially is to do with the frequency, are in your summation. Now the key thing with this Fourier summation term is that this only applies to what's known as periodic functions. And this can essentially be described as one which repeats over a certain length interval or a certain x interval. And this can actually change, this just depends upon convention. But sine and cosine you can consider as example of periodic functions, where if you have sine of x plus 2 pi, this will just be exactly the same as sine of x. And of course, same goes with cosine. So these functions are essentially repeating themselves every 2 pi. And how this relates to this summation term is that these have actually been chosen, and this is a bit of a convention thing, such that f of x plus 2l is equal to f of x. So in fact, the functions which we're dealing with are periodic, and the complete period is in this case 2l. So we can say that it's spatially periodic with a period distance of 2l. So some textbooks may drop the factor of 2 and therefore just have this included within the cosine and sine terms, but this is just the convention that I'll be working with right here. So what we can do is we can actually rewrite this Fourier series function, this Fourier series summation, in terms of exponentials. And the way that we do that is we use Euler's formula. And Euler's formula says that e to the ix is equal to cosine of x plus I sine of x. So we can rewrite our big f of x formula, our Fourier series formula, in a slightly more compact form. And this is essentially saying the same thing. However, there's two main differences. The first one is we have this cn term rather than an and bn. And it's very similar in concept. It's kind of like a weighting term for each exponential of each frequency. And the other difference is that we go from minus infinity to infinity this time. And the reason for that is that with our previous formula, because of the way that cosine and sine are defined, you essentially have redundancies in odd and even functions, whereas this is not the case with this function. E to the minus ix is a flipped version of e to the plus ix, and so both must be included. So let's just go ahead and for completeness, I'll write out what Cn is in case we're a little bit vague on that. This is equal to 1 over 2L multiplied by the integral of f of x between minus L and L, I should say, times e to the minus in pi x over L with respect to x. And essentially you can kind of think of that as the sort of product of fx, the sort of overlap with f of x with this exponential term right here. It's technically referred to as a convolution product. It's sort of like the function f of x weighted by this exponential term right here. And that's what gives rise to Cn, which is in fact our weighting term right here. So now that we have that, let's go ahead and just recap what we had previously. So remember I said that you can get any translation within a crystal structure, T, and you can say that this is an integer number, u times a1, which is one of our lattice vectors, plus another integer times a2, plus another integer times a3. And remember, a1, a2, and a3 are our primitive lattice vectors, which apply for a three-dimensional lattice. If it was a two-dimensional lattice, it would just be a1 and a2. But for a three-dimensional lattice, it's a1, a2, and a3. And I'm aware I'm doing a slight notation change now. I was using A, B, and C rather than A1, A2, and A3. This is because I don't want to use up too many letters just in case. Now, within a crystal structure, we can say that 2 points are equivalent when they are separated by sort of this T factor, which can be any integer multiple of these three primitive lattice vectors. And so mathematically, we can write that as some random position r with a prime on it is equal to r without a prime on it plus t. So what this is saying is if we translate our initial position vector r by this t term right here, if we add on this t vector right here, then we get r dash, and in this case r dash and r should be equivalent in terms of all physical properties when moved by a factor of t. So this essentially is the condition for periodicity right here. Now, what we're going to do is we're going to have a look at the number density n of electrons at a position r within the lattice. So obviously within a crystal lattice we have ions and electrons typically. Now electrons are quantum particles, and so therefore rather than behaving in an individualistic deterministic manner, they behave in a collectivistic probabilistic manner where you can at best predict the probability distribution of finding an electron at a particular point in space. So in terms of kind of bulk collective behavior, we kind of talk about n, which is the number density of electrons. So it's the number per unit volume, and this will change depending on whereabouts you are in the crystal. And so, like I said, because our crystal is periodic, if we apply a translation vector to our number density function, then what we should find is this is exactly the same as where it is beforehand, because our crystal is periodic with this t vector. And because it's periodic, well, we've essentially just shown that we can use a Fourier series in order to represent a periodic function. We kind of already know what the period is because the period, our spatial period, is just one unit lattice cell. After that, every single thing repeats. So obviously right now we're in 3 dimensions, and what I'm actually going to do is I'm going to reduce this down to a one-dimensional mathematical analysis. So in one dimension, we have instead of having n as a function of r, we have n as a function of x. So this is now just n as a function of x, and I'm just going to label this with a little subscript x. So using our Fourier series, we can say that this is equal to going from let's just use a dummy index j, minus infinity to infinity of nj, which is essentially our weighting coefficient, like our Cn right here, times e to the ij pi x over a. And that's the key thing. A now is our periodicity. So what I'm going to now do is I'm going to define k in the x direction, because of course we're only working in the x direction, as being equal to 2 pi j in the x direction, there should technically be a little subscript there, divided by a right here. So rewriting this out, this summation is going to turn into this right here. And now you can kind of see what this k term actually is. This is essentially the wave number term, which is essentially inversely proportional to the wavelength. K equals 2 pi divided by the wavelength. But oftentimes we just tend to use k rather than lambda, just because k can be generalized more easily into a vector right there. So that was one dimension, and in 3 dimensions it actually becomes a fairly easy task of just multiplying each component together. And the reason why we multiply them is that you can kind of consider the number density similar to a probability function, because the positions of electrons are described by probability distribution functions in space. And in order to get the total probability, you multiply probability distribution functions. So probabilities multiply, and therefore we can write that the total electron density in 3 dimensions is equal to the product of each component right here. And if we expand out each one of these, we get this right here. And what we can do is essentially combine these 3 exponential terms, which multiply together, and get this right here. And as you notice, we can actually write this, kind of write this back in a more compact form, which would be by defining g as being equal to kx in the x direction plus ky in the y direction plus kz in the z direction. And I'm very sorry, I forgot to multiply all of this by this n right here. So this sum is over, so there's 3 summations going on, and all of these terms are inside the sum right here. Cool. So now we get this result right here, which is much, much easier to write. So essentially what we've done is we've ended up with this kind of g vector right here. And what is this g vector? Well, we can see that it comprises of individual wave numbers in each direction right here. And we can essentially see that if we take the dot product of g and r, our position vector, then we get a dimensionless quantity, because of course the term within an exponential must be dimensionless. So in a very similar way to how we can represent a point in real space as being equal to this right here, we can actually represent a point in this kind of g space right here very, very similarly. And what I've done here is I've written the g vector out right here in terms of the 3 Miller indices that we defined last time. And the reason I can write it in terms of that is because, of course, h and k and l are inversely proportional to space. Remember when we did all this Miller plane stuff, then it was actually, I said to invert the h, k, and l values so that you could get your values of the plane. So this h, k, and l are kind of inverse space terms, and A1, A2, and A3, in a very, very similar way to how these vectors describe a cell in the real world, this A1, A2, and A3 describe a translation in this kind of G world. And we call this kind of G world the reciprocal space right here. Now, obviously, this seems kind of a bit abstract at first. So why are we kind of defining this kind of reciprocal space in these 3 seemingly arbitrary different vectors in order to describe what this G is going on right here, which is to do with the wave number? So why are we doing this? Well, G essentially can represent something which a lot of physics actually underpins. And it's actually really helpful to consider this reciprocal space right here in terms of a lot of quantum mechanical stuff. See, as you can see, this G right here has the three wave numbers in either direction. But in quantum mechanics, things such as electrons can behave both like a wave and a particle. And so if things start behaving like a wave, then we actually kind of need to define things in terms of wave numbers right here. And that's where this kind of G vector, which is sort of translating between these kind of arbitrarily defined cells in reciprocal space, becomes really, really, really useful. But of course, G is kind of meaningless until we know that it can actually preserve the translational symmetry in the real space. So essentially, we said earlier that n of r is equal to n of r plus t right here. And just writing this all out, we say that this must be equal to n of r plus u a1 plus v a2 plus w a3, using the definition of r right here. So writing out n, our periodic function, as our summation, we get this right here. So as you'll notice, the exponential right here, you can actually kind of separate this into two separate terms. And when we do that, we get this. So we can see that the only way in which we can actually make this equivalence hold is that this exponential here, this e to the I g dot t, this has to equal 1 right here. Because if this does not equal 1, then this entire equation does not balance. So we have this condition where e to the I g dot t is equal to 1. This has to be the case in order for G to have translational symmetry. So what does that mean? Well, if e to the I g dot d equals 1, then what does g dot t have to equal? Well, as we know from our famous formula, e to the I pi equals minus 1, if we in fact square both sides, then we get e to the I pi all squared is equal to 1. And then this 2 just becomes embedded within the argument in the exponential. So we have e to the 2I pi is equal to 1 as well. So therefore this g dot t term right here has to equal 2 pi, or not just 2 pi, but an integer multiple of 2 pi, which we can just use j as we've been using so far. So g dot t has to be an integer multiple of 2 pi in order for g to have translational symmetry within the lattice right here. Now, essentially the way in which you can kind of solve this is by writing out both vectors for g and t in full, but I'm just going to go ahead and jump straight to the solution because it's kind of not too hard to see how it comes about. And essentially what we find is that g, in terms of our reciprocal lattice vectors, which we had previously, and t, in terms of our real lattice vectors, these are related by the following set of equations right here. And of course, this is a system of 9 equations, which takes a lot of mathematical analysis to actually solve. But like I say, I'm going to jump to the main solutions where we can actually write the reciprocal vectors, so this capital A1, capital A2, and capital A3, in terms of the real vectors like following. And yes, that was a lot of writing out, but here you go. This is how you get from real space, so these lowercase a1, a2s, and a3s, into reciprocal space, which are these capital A1s, A2s, and A3s right here. And you'll notice that each one has a common prefactor of 2 pi, and each one is actually divided by this A1 dot A2 cross A3. And hopefully you guys remember that that is in fact the volume of the real cell in real space right here, A1 dot A2 cross A3. So let's go ahead and draw out this kind of new lattice that we've made, this reciprocal lattice. Well, let's go ahead and start with the origin point. we actually call the origin point, for a bit of an unknown reason, gamma right here. So rather than 0, we typically refer to it as called gamma. A little bit weird that, but there you go, that's physicists. And here I'm actually just going to only draw out 2 dimensions, but in theory you could very much draw this out in 3 dimensions. And here you'd have your A1 and your A2, capital A1 and capital A2, looking something a little bit like this. So you'd use A1 to translate to the right in this case, and A2 to translate up or down. But remember, this is not real up and down, this is reciprocal up and down. And similarly to how you can find the unit cell in real space, you can actually find the unit cell in reciprocal space right here. However, this has a little bit more significance to it in terms of physics of what happens within a crystal. And typically, rather than just kind of joining together cells like we did previously, what you actually do is you actually do what's known as a Wigner-Seitz construction. So this might sound very technical, but it's not too advanced. And I'll show you how to actually do a Wigner-Seitz construction. Essentially, what you do is you take your origin point right here, and you connect each adjacent lattice point, which in this case is a reciprocal lattice point right here. And then what you do is you take the halfway point among each connection right here. Then what you do is you draw an infinite line which perpendicularly bisects each of these connection lines at the point of the dot right here. So when you do that, you get this. And the region that is enclosed by this bisection, these bisection lines in here, this is known as the Wigner-Seitz cell. Now it's worth mentioning that a Wigner-Seitz cell is a primitive unit cell because of course it only contains one lattice point at the center. But in reciprocal space, we actually consider the point around the origin as having the most significant Wigner-Seitz cell, and it's actually called a name. So this region right here, in reciprocal space, the Wigner-Seitz cell, the unit cell in reciprocal space that is about the origin, this is known as the first Brillouin zone. And this is actually where most physics happens within condensed matter. You actually can sort of reduce your entire crystal structure down to looking at what goes on inside the first Brillouin zone. The fundamental reason why you can do that is because it's periodic. Crystals are periodic in real space, and therefore in reciprocal space it should follow that they are also periodic. And the reason why in reciprocal space this is especially important is because you can get some quite interesting physics happening as a result of this periodicity. And this is what we're going to talk about a lot more in upcoming videos. But the key thing is the first Brillouin zone is actually where a lot of the physics happens, simply because it has to. It doesn't matter where you go within your crystal, things have to be periodic. So if you just reduce your entire domain down to just looking at what happens within a cell in reciprocal space, and real space for that matter, then you should have all of the physics you need. So we're going to touch a lot more on that in upcoming videos, because I'm aware that the reciprocal space and the first Brillouin zone are quite advanced concepts to initially get your head around, but I hope that kind of makes some kind of conceptual sense right there. So to finish up with, I'm actually just going to talk about a few interesting properties of the reciprocal lattice. And as one might expect, if you were to take the inverse of the reciprocal lattice, well, you should end up with the direct lattice yet again. And thankfully, that is what happens. If you invert the reciprocal lattice, you get the direct lattice. And the final key one is that if we have, say, a plane in the direct lattice, a Miller plane, the primitive vectors of a reciprocal lattice are normal to the Miller planes in the direct lattice. And that should kind of make intuitive sense, given that G is equal to H A1 plus K A2 plus L A3, given that H, K, and L are the Miller indices right here. And the final quite interesting property that is worth mentioning about reciprocal lattice, and this is quite a specific example, is that the reciprocal lattice of a face-centered cubic is in fact a body-centered cubic lattice in reciprocal space. And vice versa, the reciprocal lattice of the body-centered cubic is the face-centered cubic right here. So that's just a specific example in 3 dimensions. You hopefully shouldn't have to draw that out because that would be horrendous. But when you do all the maths, you end up with that happening right there. So there we go. That brings us to the end of the first kind of really big, long video in our condensed matter physics video series. In the next lecture, we're actually going to go into the quantum world and see how the quantum mechanical world actually really, really closely ties in to this concept of the reciprocal lattice. And this is where things start to get really, really weird, but also, I think, really, really cool in condensed matter. So I hope you guys found the video informative, and see you then. Bye-bye.